Two big themes in lectures that are coming. Well, there's several lectures on signal processing and in particular on wavelet developments. So that's a half dozen lectures that are sort of a unit in the course. The other major theme is, maybe the right word would be optimization. How do you identify and compute an optimum? Of course, in freshman calculus, you have a function f of x. You take its derivative and set it to 0. Now, we got to move up from there to functions of several variables. So we got partial derivatives, and I'll start with that today. And then functions of functions. So where the unknown that you're looking for is not just a point, but a function, a point in function space, we could say. So continuous variables, and then constraints, as optimization when there are constraints on the allowed, on the admissible choices. That's a big subject, and it's partly a world of its own, optimization. It's funny, math meetings, there's linear people who do linear programming, operations research, numerical optimization, and that's a different world from PDEs and physical problems. But anyway, maybe it shouldn't be such a different world, and we can connect them. Okay, so today, let me start with a problem that I'll just copy it up here again. Minimize a quadratic. So start with quadratic functions. I guess here's one general theme, is quadratic minimum problems. And they ought to lead to linear equations. And probably that's the form that you solve them in. And many times that's the form that you create them in, you formulate. But there are other problems that are formulated as minimum problems, like this one, minimize, let me call it P of U for potential energy, or total energy, really. There's often, we need this quadratic term, U transpose KU. This is our stiffness matrix, positive, definite, symmetric. And then source term, which will be linear. So you see, this is a quadratic function of U of all of the vector U, of the n components. So here's the quadratic part, here's the linear part, and the natural question is, where's the minimum? What value of U gives the minimum? I'm going to just jump to the answer, jump to the equation for the minimum there. Because we've touched on this topic before, and it's easy to check that it's the minimum. But can I first ask you, I use the words positive definite about K, about that matrix K in the middle. What's the connection of positive definite with what you see on the board here? What is it that positive definiteness of this matrix tells us? It tells you it's a minimum. That's right, exactly. It tells you we're dealing with that when we find, if we set the derivatives to 0, and that's one, that's one way, the calculus way would be just set the derivatives to 0, find a stationary point, then that's a minimum point because that's positive definite. Right. That's it, exactly. Okay, and what is that point? what's the equation for that point? Well, the equation is KU equal F. Well, you can see that when I take the derivatives of this thing with respect to u, the partial derivatives, I'm going to get the components of F. And when I take the derivatives of this quadratic with respect to u, with respect to each of these u's, I'll get the result comes out to be KU. So that's our winner. That's our winner. Okay. So that's going back to early in the applied math book. Okay, I want to move to a constrained problem because that's more subtle. And let me take a minimum again. So I'm going to use a quadratic, and my unknown now is going to be, it's just natural, as you'll see, for us to pick the other variable. This would be like the potentials in a network problem, and this would be like the currents. So you'll see a W transpose, our C inverse W. That's the energy, the heat generated by those resistors, or the potential energy in the springs. But of course, what's the minimum of that? Just so we see where the constraint comes in. So what W would minimize that expression there? 0 would. Right. But somewhere we ought to have. I want to connect this problem to this one. And this problem had a source term, namely F. And here the source term enters in the constraint, and the constraint is, so you see that we're on in our famous diagram of u's and the vector A that takes us to e's. That was up here. Now maybe I do dotted line. C is the connection to W's. And then to A transpose, and the equation A transpose W equal F, the balance equation. We have had a bunch of examples of that, and I could multiply those examples. So this problem, you didn't see any W in. This problem, you don't see any U in. But I want to, let me just ask now this question. How do I find the minimum when I have to obey some linear equations? How do I find the minimum when I have to obey some linear equations? And let me give a specific example of this type of problem, and then we can think how to solve it. So an example will be distance to a line. Okay, so I'm going to be in there's some line. I'm in W space, W1, W2. And I have some line like, well, I don't know what that line looks like. It has a slope of 1, so maybe W1 minus W2 equals 2. Does that seem a conceivable equation for what I've drawn there? Or should it be a plus? I guess plus, is that? Minus, was it? You see a holiday in France and you don't know plus from minus. Is that right? Yeah, minus looks better. And was it reasonable when W2 is 0, W1 is 2? That's reasonable. And when W1 is 0, yeah, thanks. That's fine. Okay. So what's our problem then? The distance to a line, we're minimizing. So what quantity am I minimizing? And where's the winner? Let's see how this problem goes. so I'm minimizing distance. So I'm taking any point on the line. Here's a typical point on the line, and distance to a line from the origin, from 0, 0. Right. Thanks. So, all right, now that's stated. So there is one point, but not the closest point, certainly. But that distance then is, we're minimizing W1 squared plus W2 squared, right? Distance squared, we could say. We're minimizing distance squared, subject to the condition that we're on the line. Okay. How to do that problem? And you see that that's an example of this. And it's an example with C. What's the matrix C in this case? Just the identity. And what's here I have W. Let's remember, if we follow our convention, should have M components. And we're imposing N equations, N constraints. Let me call them constraints. Right. So over here, M is 2. There are 2 W's. And N is 1. There's one constraint. So that now I have here an example of that. And we could ask, let's stay with this example for a moment and then come back to the general case with the sort of the case with letters. Here's the case with numbers. Okay. First of all, tell me where's the winning point? Where is the W geometrically?
1 minus 1.
Oh, you've got. I see. Is that? Oh, all right. And so what is special about 1 minus 1? I'll put it in. It has a right angle, exactly. It's the point that's where that's at 90 degrees, and that's the winner. Shall we call it W star for the winner? And I think you must be right. It's 1 minus 1. This is working out even better than I wanted it to. Okay. So you could see that wins. But how to approach problems like this? So now I ask you the question. How do I deal with a constraint? How do I deal with a constraint? I could think of well, open to suggestion. I could just substitute. I could just say, okay, this constraint tells me that W1 is 2 plus W2. So I could change this. I could solve this. So I could say W1 is 2 plus W2. And then I could say, okay, I'll minimize. Then W1 squared is 2 plus W2 squared and the W2 squared. Okay. So I'm back to an unconstrained problem. I got the constraints out of the picture by solving for W1. Now, that certainly seemed like a pretty good way to do it, but but it's not the way I want to recommend. And so the way I'm going to recommend is associated with these Lagrange multipliers. So I'm going to build the constraint. What I'm actually going to do is bring in a new unknown. What seems kind of expensive or I mean inefficient to. Here we've got 2 unknowns. This reduced it to a 1 unknown problem. That was certainly looked great, and instead I'm going to go the other way, and I'm going to say I'll minimize. I'm going to keep this quantity that I'm minimizing, And then I'm going to subtract off this constraint, W1 minus W2. Let me put the 2 on the same side and multiply this by some mysterious shadow multiplier that I'll call U. So this is the, and lambda is often called lambda, but for a reason you'll see, I wanted to call it U. So this is the famous Lagrange multiplier. So it multiplies the constraint. Now I have a problem with 3 variables, W1, W2, and U. And I want to take the partial derivatives with respect to those 3 variables. That'll give me 3 equations when I set them to 0. And then I'll solve for W1, W2, and U. And will they be linear equations? Yes, because I've got second degree stuff here when I take derivatives. So let's just do that. Take the derivative with respect to, first the derivative with respect to W1. What do I get? I get 2 W1s minus a U equals 0. Is that right? I set the derivative to 0. Now the derivative with respect to W2, I'll get 2 W2s. The derivative with respect to W2, this is a plus U, is 0. And finally, the derivative with respect to U is what? It's the constraint pops back. So that you could say, well, certainly safe in that respect that the constraint popped back W1 minus W2 minus 2 equals 0, and let me move the 2 back onto the right-hand side. So there was a d by dW1, here was a d by dW2, and that was the d by du. 3 equations. I guess I should ask now, there's something not quite right on that board at the moment. And what's not quite right is that those letters, min. They're right here. It's the minimum of W's. But now when I bring in this U guy, this Lagrange multiplier, it's not, you see, it's not positive definite. If I wanted to make this small, I would make this guy minus, I'd sort of make this guy far off, and I could, well, so what I'm trying to say is, this is really, I don't know whether to cross out min, because I shouldn't, it's not a minimum over the, it's really a minimum over the W's still, but it's probably a maximum over U, I think. Yes? Oh, yes, let's see. I think it's okay, but I did play quick with that minus sign. So if I take the derivative with respect to U, yeah, let me do it right. And then I think if I take the derivative with respect to U, there really is a minus sign. That's true. Minus the W1 minus W2 minus 2 should be 0. That's the d by du written right, written correctly. Now I ignored that sign and I moved the 2 over there. Yeah, sure. No, I did it too quick. Just to say, what would happen here? Can we, before I go any further with that example, can I do the same thing here? So this minimum problem, I'm going to introduce, maybe we better give it a name like L for Lagrangian. So this is the Lagrangian. This is, so I won't put max or min, I'll just define it as L as, this is has the W's in it and has the U in it. And it's the key quantity. Before I forget, I have to justify in some way, doing this, making the problem more complicated, where here we had a way to make it so simple. So that was so simple. And why would we? So this is the simple way, but there has to be a but. And I'm trying to think how to express the but part. Somehow, what did we have to do to get there? Well, we had to express some of the unknowns in terms of other ones. We had to solve the constraints. And that's what I want to say is not so easy in general. This simple way, but you have to, but need to solve the constraint equation. Find the solutions. You could say it's, and it's not, there are problems where this is a reasonable way to go, and it's called the null space method or something. Because you've got to deal with this A transpose, W equal F equation, which means, you remember, what's going on with this equation here, this constraint equation? It's n equations with m unknowns, and m is bigger than n, of course. So we've got some degrees of freedom here, and the problem of identifying exactly what are those degrees of freedom, which w's should be solved in terms of which other w's, is not easy to do it systematically. And if we had nonlinear equations, like with log w's or e to the w's or sine w's or something, then we couldn't solve for some w's in terms of others. So Lagrange has really got a better way. So the Lagrangian takes the thing that you're minimizing and then subtracts off, introduces this multiplier, u, times the constraint, and says, okay, build in the constraint into your function. That's what Lagrange has done. And if you've seen and used Lagrange multipliers, then I appreciate your patience, because this is the most basic context for those. Now, there's one thing I have to fix here. How many constraints have I got? N. How many Lagrange multipliers have I got? I need n. Each of those equations deserves its, so the first equation should get multiplied by u1, the first Lagrange multiplier, the second by u2, and there are n different Lagrange multipliers. I'm going to end up with L. This guy L is a function of all the w's and all the u's. So there's m of these guys and n of these. This is how many unknowns we've got now. M plus n. M original w's and n multipliers, because we've got n equations here. So now, can you tell me how to fix up what I've got there? Transpose. I want the inner product between all n of the u's and all n of these, of that column. Right. Now it's right. Okay. So does that copy for the general quadratic linear case this example for the specific distance to a line problem? Now, shall I go back to that distance to a line problem? And because the beauty of Lagrange is his method produces these equations. We didn't have to we didn't have to untangle these constraints at the start. We're getting that system. Okay, what's the solution to that set of equations now? I'm hoping that it's the right answer. So what are W1, W2? It's 3 linear equations in 3 unknowns. It's produced in a systematic way, and we can solve it in a systematic way, but actually in this example, since you already started me, we can solve it by sight. What's the answer? W1 is what? W2 is what? U is what? So W1, the correct W1 is 1, thanks. And the correct W2 is -1, and that agrees with what you identified as the winning point. Now we get some more information, which is what, the U, and what does the U come out to be? 2. All right. So we got some more information, except we don't know what it means, right? But it has a meaning. Very important meaning, actually. This 2 has a very, very significant meaning. So this is where Lagrange has a lot of subtle stuff in there. And so at one level, Lagrange is just telling you how to deal with a constraint. What he says is, build it into the function. But at another level, he's got that's not just some arbitrary. When we find its values, in this case 2, they have an interpretation. Maybe I mentioned in economics, these would be called shadow prices. And I won't try to digress and explain that, but those are prices that are kind of in the background. Let me, well, so what do I want to say? Can I tell you what that U does actually represent? At least have a shot at it. So I'll take two or three different comments about the Lagrange multiplier. And here it's just a single number because n was 1 in that example. Let me see. I've almost solved the problem. What I guess I haven't done is actually written down the you found the best W, but what was the minimum then? What was the minimum for W1 squared plus W2 squared? The thing that we were trying to make small? Turns out to be, what, 1 squared and minus 1 squared? 2. All right, now, please. That's not you. That's not you. I'm sorry. Not the same as you. Not the same as you in general. I mean, of course, 2 is 2, but it's not, wasn't meant to be. All right. Now I'm going to say what this U represents. The U represents, it's sort of the derivative of this answer with respect to a change in the constraint. Gosh, can I try to put that down in words here? What one meaning for this Lagrange multiplier is it's the rate of change of the minimum value with respect to changes in the data. And the data here is the F, the 2, the F. In other words, I think that if I change this to well, if I change it to 2 plus epsilon, what will happen? Suppose I change that 2 by a little bit. Then what's different about my problem? I'm not going to change this part of the problem. I'm just changing the constraint a little. If I change the constraint a little, what happens to my picture? that line moves. The line moves, right? So here's the line, here's the 2 plus epsilon line, right? And then the winning W wouldn't be the same anymore. The winning W would be on the new line, of course, has to be on the new line. And the minimum value would be a bit more. And my claim is that it would be about U times epsilon more. And maybe, actually, we could even see that here. I've never carried it as far as this, but shall we have a shot at it? Yes. Yeah. Well, right. Right. I think that if I move that line a little, then the winner, what would the winning point be? 1 plus epsilon over 2 and a minus 1 plus epsilon over 2? Or minus epsilon over 2, okay. And then I would, I'm hesitant. This is going further in this lecture than I want to get, and I want to get to the continuous calculus of variations. So can I chicken out and just leave you with this wonderful fact that the Lagrange multiplier has a meaning, and this is one of its meanings. Okay, I've got to follow through in this general case what we did with the numbers. I got to do now with letters. Okay, tell me the equations I get when I take derivatives set to 0. What equations do I get when I take the W derivatives and set them to 0? Here. So what equation will I get when I take the W derivative and set it to 0? You remember how this one went. The derivative of that gave me a KU. So what's the derivative of this guy going to give me? Just C inverse W, right? I mean, it just, if this was scalar, 1 by 1, this would just be 1/2 W squared over C, and the derivative would be W over C, right? And now what about the W, what's the W derivative from here? AU, good. AU, perfect. Perfect. Should equal 0. And now what about the U derivative? That's the other rule here. So this is setting one derivative to 0. Now tell me what the U, so this is M equations. Now I need N more equations, and they come from the U derivatives being 0. And what do I get when I set, this is the easy question, I get that constraint back. A transpose W minus F, and again I'll put the F onto the other side. Huh, okay. This is like supposed to be the golden moment here in the lecture. That this problem, which looked different from this one, it did use the same stuff. It used the same stuff because the K in this problem was A transpose CA. We didn't say it, but we understood it. So the data up here is these matrices C and A and the vector F. And the data down here is the matrices C and A and the vector F. And my point is that I got to this system of equations. This is exactly the letters case for this being the numbers case. Right. And now what? Now I've got to solve those equations. So just start me out. How do I How shall I solve this system of equations? I'm hoping this looks familiar, even though it's been a month. Solve for, yes, solve for W, good. So how do I solve this first equation for W? And what does that tell me? Have I got just, I think I've just got space here. You see, I haven't lost the knack of using everything. All right, so I solve that equation for W, and it tells me that W is what? CAU. Good, which we remember, right? W, look, you see this framework. What this is doing now, what I hope is going to happen is we're going to see that it's the same problem. We're going to see that this problem, which sort of was associated with this part of this side of the framework, gives the same set of equations as this problem that was associated with this part of the framework. And what's more, we're going to identify what the Lagrange multiplier U is physically turning out to be. It's going to turn, right? It's going to be this guy. This Lagrange multiplier that came out of the blue is actually the potentials for in the network example. Now let me just finish here. If W is CAU, that was great. And now I plug that into this, right? And I get A transpose. Now W is CAU equal F. And sure enough, that's the same as that. Right. So I could present Lagrange multipliers just as a device, but that would be to miss the beauty of that idea. It is a device to build the constraint in and lead to equations, and you see that if the constraint had been nonlinear, that wouldn't have baffled us. We still would have had its Lagrange multipliers. We still would have taken derivatives. We would have got nonlinear equations, but they'd have been ready to solve. So Lagrange's idea is really very general. And you'll see near the end of this series of lectures that we could even deal with constraints. Now this is going to be, I'm going to make this constraint nonlinear, not by taking logarithms or sines or exponentials, but by that device, by making it an inequality. Now I have, that's a nonlinear constraint. It's sort of like pretty close to linear, but it's not linear. And yet Lagrange can deal with that and will deal with it. So linear programming, quadratic programming, that whole world of inequality constraints, Lagrange is up to, where our simple method would just have wiped out. Okay. Yes.
Does it matter to subtract that multiplier constraint or add it?
No, it doesn't. And I for a moment I was wondering what did I do in the book, and I wouldn't be surprised if I did it with a plus in the book. And we remember and that would have produced a plus there, which is what we would have been. We've seen it with a plus. Yeah, we've seen it with a plus. Right. Right. Yes. So yeah. So that's really just a convention, whether to build in with a minus sign or with a plus sign. Both equally good, and I shift from one to the other. Yeah. So can I just recap? My point is that whenever you have an optimization problem, you have two problems. That's a way to say it. And that other shadow problem you might not see. And you might, if it's just a straight minimization, you probably don't want to see it. You just minimize this thing, go for it. But there is that second problem back there. And here, in this form, you've got to see it. We're minimizing something with a constraint. We have to deal with that constraint. Lagrange deals with it by building it in and increasing the number of variables, increasing the number of equations, but it connects back to the other. So there's what I mean is that there's a problem called primal, which is probably natural to call that one the primal, and there's another problem around hiding in the shadows. It's the dual problem. Optimization problems come in pairs. Can I even try to describe a problem that's sort of dual to this one? Let me get back to my original question here. Let me move up a dimension. Let me move this into 3 dimensions, just to describe geometrically a dual problem, because they're quite fun. This relationship between primal equals dual, and there's a theorem called the minimax theorem that gives the connection. That's duality. I'm putting words on the board that I'm going to elaborate on in future lectures. Sure.
I think we're getting to I can't really see why the Lagrange formulation is equivalent to the first formulation.
To this original one.
Why does the constraint have to be true?
Well, because, so I can give a partial answer. Why does the constraint have to be true? Let me get the epsilon out of it. Because it showed up. So by building it in this Lagrange way, when I take the derivative with respect to u, that's bound to throw me back, throw the constraint forward.
I don't see why the W's have.
You're.
How do they get designed so they're both true?
That's excellent question. So I was answering the easy question, that the derivative of u will bring back the constraint. That's just, we built it in that way. We multiplied the constraint by u, so when I take the u derivative, out will come the constraint. That's easy. The real question that you're asking is not easy, is why does this work? Yeah. And I don't think I'm up to answering that today. Yeah.
Well, use a constant in some sense with respect to W1 and W2, so we think there is.
Yeah, you can, anything you say, I'll nod my head, but.
Guarantees that you don't add, when you satisfy that constraint, you're not
Right.
adding anything to this function.
Yeah.
Because that goes to 0. And then you're just taking derivatives with the other two variables.
Well, that's right, but somehow this u magically, that we built it in a way that it showed up here, and that's really a question. I mean, where the heck did it come from, and so on.
The thing is, any u will cause the constraint to be true. But you only end up with one u, which causes W.
Which makes everything perfect, which is the winner. Yeah, that's right. Thanks for that question. I mean, you might say, you might say, well, why not answer it? But and I haven't. It's a more subtle question than I am prepared to answer.
Another problem. You're in a subspace, a section across subspace.
That's true.
You're bringing yourself to all those variables.
That's right. If I wanted to, that suggests a picture that I could draw for this problem, which might ultimately give us some insight to answer your question. What would be the picture that I would draw? Well, one picture is this picture, but let me draw a picture in. Let me draw a surface. So what have I got there? That's one of my favorite bowls, right? Circular bowl, because we've got the identity matrix. So if I graph W1 squared plus W2 squared, it's one of these guys, right? And what's the minimum? 0. Okay. But now impose the constraint. So what does the constraint do in this way of looking at the problem? So here is W1, W2, and I'm graphing W1 squared plus W2 squared, this thing that I'd like to minimize. But now, what is this constraint, W1 minus W2 equal 2? What is, so I've got this nice, beautiful Chinese bowl. Oh, I'll have to bring you what I brought back from China. Excuse, you'll allow this digression. Two interesting things on the plane coming back from China. One was Henry Kissinger. Well, excuse me, Henry. But he was in seat 1A, so I wasn't quite across from him. But I had a word with him at the, he collected his own luggage at the carousel in San Francisco. So anyway, it had been 30 years since his first, that historical visit to China. So that was one thing. The other thing was something I brought on the plane. I'll bring it in to show you, if you're willing. It's a Chinese teapot. I won't spoil it now. Nor will I use up more of the lecture to tell you about it. But I will bring it with me next time. Okay. You'll smile when you see it. Okay. Now, where am I? I want to build this. I want to say, okay, in this picture of the problem where I'm looking at the minimum point on the surface, but now I'm imposing that constraint, what does that constraint do? Exactly. Good. And that Bob's question brought it out. This is a vertical plane, W1 minus W2 equal 2. There's our line. This is the same line as in that picture. And there's a slice coming down, so we're really slicing through so we're slicing out a kind of parabola, and the winner is the point. There's our winning point, 1 minus 1, and the winning height was whatever we decided it was, 2, I guess. So I mean, that's really nice to see that bowl with the vertical slice coming through it. That's something in 3D that our eyes can visualize, where we would have the beauty is Lagrange gives this mechanical approach where we don't really have to think in high dimensions. We just do what he says and out come equations. But you're totally right. Since I'm emphasizing that it's not purely mechanical and that his multipliers have a meaning, then your question is totally right that what is that meaning? What's going on? So maybe it's good that this isn't the last lecture on optimization. We'll see Lagrange multipliers. We'll see inequality constraints and linear programming, all those things. We'll see duality. Maybe if I've achieved two things, one is what's the system, what's the mechanical system, and the second to sort of whet your appetite with what's going on. What does you really mean? Then I'm happy with that outcome of here's the way to introduce Lagrange multipliers, and then I gave some kind of a meaning to them, the change in the answer with respect to change in the input data. It's fantastic, and that's what Lagrange has achieved. So but to see the whys, I haven't tackled that in this lecture. Okay. I have a little time left in this lecture for the continuous time, the function equivalent. You take a deep breath. I'll do the same. And I'll make a little space. Can I try to give the corresponding problem in continuous time? Okay. So there, you can reckon, and let me put a yellow thing around the two problems. One problem was minimizing this, right? And we'll be pretty happy if we can turn that into continuous time. The second, the dual problem was this one. And we may not have time to discuss its continuous analog. So it's these problems in discrete for n variables and m variables that I now want to say, what happens if the unknown is not a point but a function? Okay. And of course, and our framework is going to work. What will A be in our framework now? This now U is going to be a function. Let's go to the most basic example. You remember what was the most basic example? A became d by dx. You remember that? And A transpose became minus d by dx. So we had differential equations. What was the differential equation? What was this equation? Let's just remember what it is we're doing. This equation for when A was d by dx was, do you remember that? So the A transpose was minus d by dx. Then we had the C of x. And then the A, which was d by dx, of U equals f of x. That's the equation, the linear equation. That's this. Okay. Now all I want to ask is, what's the minimum problem that it comes from? What's the continuous analog of this minimum problem? So this is going to be our winning equation. This is going to be the equation for the winner. And I'm working up here now, and not the constrained case, just the easier unconstrained case. This picture is still relevant, but now I've got to think, what's P of U? So what's P of U? So I remove this example and make space for P of U in the continuous case. Okay. Okay, so now I'll put up here in the yellow letters, continuous variable. The unknown is a function, U of x. And what's the P? What's the thing that we're minimizing? We're minimizing some P of U. Can you convert that with K as A transpose CA? So let me make K into A transpose CA. So I want to convert that to the continuous case. What's the continuous equivalent of that problem? It's okay. What do I do? What are these dot products going to be? Let's start off easily. What's the continuous version of that? Now f is a function, f of x. U is a function, u of x. What's the dot product? It's an integral, right. So this term is going to be exactly minus the integral over some range, let's make it 0 to 1 again, of u of x, f of x dx. Good. That's the linear term. That's the linear term. Okay, what about the quadratic term? So look at this way. Look at this as AU transpose C AU. Is that all right? So what have I got here then? I've got the 1/2. Now I've got a dot product there. right? So I'm going to have an integral. And what is it the dot product of? It's the dot product of AU. And I'm going to focus on this example. A is d by dx. It's du dx. The dot product of du dx, that's AU. And now what's this? Well, there's a c of x. And AU is another du dx. So it's really du dx squared, sure. Dx. Well, it's the energy. Actually, since they're both integrals, I could simplify my life with just one integral sign. And one dx. Yeah, that'll be a lot better. So minus u of x, f of x, dx. Yeah, I'll just move this dx out a little bit so you know. So this is it. This is our AU transpose C AU, and this is our U transpose F. Yeah, that's right. Sorry, what about the half? Oh, I can't put the half on the outside. Right. The half only goes with the quadratic terms. Can I squeeze it in? I can't squeeze it in there, that's for sure. Let me put it there. Yes, thank you. Absolutely right. Absolutely right. Okay. All right. So that's, what have we done? We've operated by analogy. I mean, and that's what part of this series of lectures is, to develop that instinct, that analogy between the discrete and the continuous case. Right. So dot products became integrals. Matrices became derivatives, and the unknown changed from a vector to a function. But how do I minimize when my unknown is a function? How do I find the function u of x that makes this quantity a minimum? Do you see that it's a quantity that depends on u of x? I'm looking for a whole function now. I'm not just looking for a point in space, I'm looking for a point in function space. How to minimize such a thing? Let me ask you what the equation, what you think the equation is for the minimizer. Somehow, do you see what, if you give me a function u, like sine x, I can plug it in, I get a number. Then you give me another function like e to the x, I plug it in, I get a different number. And I'm looking for the function that produces the smallest number. But obviously, what I've described is just randomly trying functions is not a recommended method. Yeah. Good. Exactly. I have to take. I need the idea. Need the idea of the derivative. Let me use a different delta of of this p with respect to u. That's what I need. And of course, I'll set it to 0. I mean, it'll be calculus, but it'll be calculus of, well, the real word is calculus of variations. So calculus of variations, all that means is move the problem up to here where the unknown is a function. Okay, so I need that idea. And I don't know that in 30 seconds I can produce it. But the main point is you see what's needed. You see that we need, well, how would you do it? Let's not even do it in detail, but just, actually, my second lecture today can build a little further on this. So let me just ask you for a thought about how to create this idea. Yeah. how would you look for the minimum, or look for an equation for the minimum? What would be a property of the minimum? I mean, so I'm really asking you, okay, be Newton all over again, invent calculus. No constraints at this point. You're allowed any function u of x. This is given. This is given. This is the data. This is the data. And you're allowed any function u of x, and I want to know which function u of x makes that integral as small as possible. And I want an equation for that function. And so I want to reinvent calculus for functions. So any thoughts on that? Yeah.
Would it work that if you go back to this original thing, all those integrals and derivatives are just linear?
Yes.
So
I'm expecting a linear, right?
with respect to u as opposed to
Yes, right.
just formally do it out.
So I'm expecting a linear equation because I've got something quadratic in u, right? Complete a square, that's an interesting idea. But now how did calculus come up with this idea that the minimum value is that point where the derivative is 0? What was underlying that idea for calculus? Right. Any change increases it. Exactly. Here's my winning point, and if I move over a little, it goes up. No, so what's a change here? U is the winner means what? If U is the winner, it means that this value is smaller than what I will get if I change U a little. Change d by dx of a little, can I change it by v? Squared c of x over 2 minus, I'm changing u by v. Any v, f of x dx. Did you see that idea? Because that's the central idea. This is got to be true for any v. Any v of x, you recognize v of x is a function now. So in other words, u plus v is a candidate. Somehow I'm taking the derivative with respect to v, right? Well, I'm taking it's. I think you should think of it. I'm at a point in ordinary calculus. I'm at a point x, and I'm trying to minimize some function f. And what's my rule? My rule is that if x is the winner, then f of x is smaller than what I get if I move a little bit. That's what led to calculus. And this delta x could be to the right or to the left. And this will lead me to the conclusion, the calculus conclusion will be that df dx has to be 0. And if I want to know that it's a real minimum, then there's something about the second derivative being positive. And this sort of square here is what's going to deal with that. But I'm at the first derivative level, finding the equivalent. So this was the calculus idea, you could say. And what is that calculus idea? The calculus idea said, well, what is f of x? What's the connection between this line and this one? Well, calculus says, okay, if you just moved a little bit, this is approximately f of x plus what? Delta x f prime, right? If my movement was just small, then there's corrections, but they'll be extremely small. So now I have f of x is smaller than this. What's the reasoning now? There would be a second order term, yes. But I'd like to, if I can just get it out of this first order, because I'm only looking for the equation. This is df dx, of course. What's the reasoning? Well, why does that have to be 0? That's what my question is. Because if it's not 0, you could move a little bit. What if it was negative? Move in the other direction. Great. That's it. That's it. That's why the derivative has to be 0. Because this delta x, you could move one way or the other way. So that if this derivative wasn't 0, then some way it's going to drop. And this wouldn't be the winner. So that's what we'll do here. That's what we would do here. We would say, okay, this can be any v. It can be positive somewheres, negative somewheres. And so out of all this, we'll identify, okay, the term that's linear in v, the linearized correction. I've carried this beyond the hour, but and I'll stop here and pick it up in the second lecture, and then go on to the finite element method, which illustrates this in a nice way. But do you see where I am? We're looking for the equation for the winning u. And by the way, what is that equation going to be? It's going to be this. That's going to be the equation for the winning u. And it's named after Euler, or actually often named after, it's often called the Euler-Lagrange equation. So somehow, the equation for the winning u, when I follow the calculus ideas, will turn out to be that equation. And then the analogy will be perfect. That has a u in it here? Yes, and this is the winning u. Yeah, yeah, so, but you're raising a good point. I'm not making a very good notational distinction here between this is p of any u. Any u is allowed for the moment, and then I'm looking for the winning one. Maybe I should give a star to the winner. You somehow indicate the function that makes this a minimum. So that's the point, that if this guy is the winner, then wherever I move brings me up. And that should lead to an equation for u star. Okay, let me pause there. If you get a chance to think a little bit about this during the 20-minute break, and pick up at 3:30. Thanks.